Okay, Kim. And then live streaming.
Yeah. No.
Webinar. I might choose it.
You could do it on Zoom technically.
No, Zoom 300 people. Yeah. 200 people. It's very bad. I tried it.
Very bad.
You just I tried it once. Doesn't make a difference. Doesn't really.
Why not?
I tried.
Why does it painful?
Anyways. Okay, let's get started. People attending virtually, can you guys see? Yeah? Is it clear? Okay, great. So the first time the work per group was like G if phi from B to H is a group homomorphism, then G modulo the kernel of phi is isomorphic to phi of G. In particular, phi is projective. And G modulo per phi is isomorphic to H, right? Because then phi of G. Okay. Okay. We'll look at the second isomorphism theorem. The third one. I'll let you prove them as an assignment. They all follow from the first. I mean, they're in the book as well, so you might just read how to do this. We'll let you be a group. And a normal subgroup of G, and H a subgroup of G. Then H modulo H intersection N is isomorphic to Hn modulo. Okay. This is the second isomorphism theorem. The proof is not that. The proof is that you consider phi is N from G to G to N. That sends Gn to that sends G to Gn. And you see what happens to H, and you see what happens to Hn. Right? Now, as your friend suggested last time, when you take phi on Hn, since n is the kernel of this homomorphism, phi of Hn will be equal to phi of H. And then you can see what happens. Okay? Okay, so I'll leave you the details. And then the third isomorphism. Now this one we will not be using much. So this one I don't think you should really worry about.
Wait, can you scroll back up?
Yeah. We good? Okay. The third isomorphism theorem is a very nice also. I don't think also we'll need it. I don't think we'll need it either. So, but it's good to know. Let's do a group. a normal subgroup of G. If H is a subgroup of G containing N, if H is a normal then H modulo N is a normal subgroup. Of the G of N. And then G mod N modulo H mod N is isomorphic to G modulo. Okay, so if H is a normal subgroup containing, if H is a normal subgroup of G containing N, then G mod N mod H mod N is a normal subgroup of GH. Is a isomorphic to GH. Now, just something here in this current homework, you have proved that Hn is a subgroup, right? If N is normal and H is in G, then Hn is a subgroup. Okay, so all of these things make sense. And you have proved that H intersection N is a subgroup of H. Okay, so I mean, also the proof is not it's not bad. I mean, I'll just give you an outline. So consider pi. Or you know what? I was at pi. Consider pi. Well, I'm not called. Consider pi from G mod N to G mod H. That sends a coset Gn to a coset Gh. Of course, you have to show first that this is well defined, surjective, and has kernel H mod N. Okay. This is the idea. I think the book doesn't show it's well defined, but I'll leave it here as an exercise to do it. Again, these are things that are not very important, but I believe it's good to see it. Okay, yes, sir. H. Yeah. No, this is a group, right? Yeah. This is the left coset because N is normal in H as well. Oh, Hn is the group you've seen in the assignment, right? If H is normal, this is just the set Hn, H and H, and N, right? Now, if H is normal, if one of those two is normal and the other is a subgroup, then Hn is a subgroup of G, right? And you have to show that Hn is equal to NH. Okay. Anyway, these are the isomorphism theorems. I don't think we really use them, to be honest, but we use the first only. The third and the second are not to be used. Well, for now, I guess. Okay. Usually they see them and not use them. I think you'll use them in algebra 3 maybe or 4. So, but yeah, here we'll just see them. Okay. Now let us move to Cayley's theorem. Let G be a group, and sim G of bijections okay, the symmetric group on G is just the group of bijections from G to G. Now, Cayley's theorem states that G is isomorphic to a subgroup G. Or in other words, there is an injective homomorphism from G. Now let's prove this. It's not it's a bit abstract, but it's things we have seen. So it's nothing we have not seen. Well,
Wait, what do you mean G is the isomorphic to a subgroup of G?
so it means like a subgroup of sim G. Thank you very much.
Like,
Thank you very much. Thank you very much. Yeah. So G is isomorphic to a subgroup of sim G. So basically, you can find an injective group homomorphism from G to sim G. Now you know the idea here is not that. It's something we have seen. So define lambda G, so let G be in G, and define lambda G to be from G to G. I think it's a function we have seen many times that sends X to Gx. Okay, in one of your assignments, you have shown that lambda G is bijective. Since I think it's homework 3 or homework 3, right? You've shown that lambda G is bijective. You remember this? Yeah. I mean, you know, what's the inverse of lambda G? Consider lambda G inverse composed with lambda G. You can check that this is the identity on G. G inverse Gx is X. G inverse times X is also X, right? Or define right from G using G by sending little g to this function lambda G. So lambda G is an element of the symmetric group on G because it's a bijective function from G to G, right? Now, if I send G to this function lambda G, I get a group homomorphism. Let's prove that. So what is phi of G1, G2? This is lambda G1, G2. Now I need to show that this is just lambda of G1 composed with lambda of G2, which is phi of G1 composed with phi of G2. Now why is this true? Well, what is lambda G1, G2 of X? Or X and G? This is just G1, G2 and X. This is just G1 and G2X. Well, what is that? This is just lambda G1 applied to G2X, right? This is the function lambda G1 applied to G2X. Well, what is G2X? This is just lambda G2 applied to X. Okay, so for all X and G, this is true. Okay, so this is a group homomorphism. Is it clear? Any questions on that? Yeah. Here, sure. Evaluate it at X. Pick a random element, X of G. Okay. So what is lambda G inverse lambda G of X? It's just G inverse times G times X, which is X. Is it clear? And you do the same thing for G inverse. It's G times G inverse times X. Okay. Great. Now I'll show this homomorphism is injected. And I think in the new assignment I asked you to prove Cayley's theorem. but I'm doing it here, so you could just rewrite the proof. And by the way, the new assignment is all extra credit, so it's extra credit. All the questions are worth marks. Now, due to the fact that you only have 4 graders, some may just be graded for completion. Okay, I'm not telling you which are graded for completion, but if you hand in, some will be graded for completion. And yes.
What does it mean graded for completion?
You just write something, you just hand in something, and I just assign the mark, full mark for everyone. Okay.
We just need to.
No, I'm not saying all the questions are graded for completion. I said some questions might be graded for.
Does that mean we can just submit a blank paper on everything and we would
Yeah,
get?
yeah. You would get something. You would get something. Yeah. You would get something. Yeah, you would get something. Now, maybe it's one question that is graded on completion, and you know that. Yeah.
Yeah.
Yeah. Exactly. So I'm encouraging you to submit something. Okay.
Submit at least.
Yeah. Yes, I extended it until Monday. If you want an extension, I can extend it further. Do you want an extension on this homework? Homework 6? Pardon me? Sure. Okay. Yeah. I'll extend it until Friday, maybe. So you have 2 things due on Friday. Okay? So the Friday one is a bonus one, but maybe the questions that are graded for completion are not too many. So like, don't rely on that. But anyways. Great. Okay, now let's show phi is injected. Phi is injected. We'll show that the kernel of phi is 1. Let G belong to the kernel of phi. Then lambda G on G. Well, what does it mean? It means that Gx is equal to x for all x in P. Hence G must be the identity. It's the kernel of phi. Is the identity. That's the identity. And hence phi is injected. Therefore, by first isomorph is a theorem. G modulo kernel of phi is isomorphic to phi G. Now, what is the kernel of phi? The kernel of phi is the identity. Okay. Now, G modulo the identity is isomorphic to G. So really, G is isomorphic to a subgroup of the symmetric quantity. Okay. Pretty good? It's a bit fast. No, I totally understand if you find it fast. But
It is.
yeah. But again, it's yes. Pardon me? Oh, I want to show that phi is injective. So I want to show that the kernel of phi is just the identity. Okay. So if G belongs to the kernel of phi, then G is the identity. Okay. Exactly. Okay. Okay. Now let's do a small application. I mean, I'll give you an homework. So I'll just give you this application, which is a really nice application. The G is finite. Okay. Now you have a homomorphism from G to symmetric G, symmetric group on G. Phi, right? And you have a homomorphism from the symmetric group on G to plus or minus 1, which is the sign homomorphism, right? The sign of a permutation. If the permutation is even, it's 1. If it's odd, it's minus 1, right? You remember this sign homomorphism from Sn to plus or minus 1? Yes? Now, so you have a homomorphism from G to plus or minus 1. So sign composed with phi, I'll call it rho, is a homomorphism from G to plus or minus 1. By just taking, rho of G, it's sine of lambda G. This is a homomorphism from G to plus or minus 1. Just the composition of two homomorphisms is a homomorphism. Now, if lambda G is odd for some G, then this homomorphism, I will not write this down because this is more in your homework. But anyways, you can listen to this. If lambda G is an odd permutation for some G in G, then this homomorphism is surjective. You agree? Because the identity is even, right? And if you have another odd permutation, then you get this sign of minus 1. So this homomorphism will be surjective. Now, if you look at the kernel by the first isomorphism theorem, the kernel will be a normal subgroup with size G over 2. Okay? I'll say that once again. If for some G, lambda G is odd, then this homomorphism is surjective. Because you get plus 1 because of the identity, and you get minus 1 because for some G, lambda G is odd. By the first isomorphism theorem, the kernel of that homomorphism is a subgroup of G which has index 2. What's a normal subgroup of G? Okay? Try to think about that. This is a question in your assignment. It's a nice question.
I'm not sure to understand the question.
In the homework, I'll give you the question. It will be laid out very clearly. But I'm just saying that if this homomorphism is surjective, then the kernel is a subgroup of G of size G over 2, right? By the first isomorphism theorem. Okay, so I'll give you a nice application to that. It's I was trying to do something once, and then I was looking at a problem from a textbook, and it was it was something. It was a nice application of this thing. You'll see on your homework, okay? I mean, you'll be able to show that if G has 2k elements, where k is odd, and G has a subgroup with k elements. Okay. Mainly the kernel of this homework. Anyways, enough talk about the homework. We're gonna have to do that. I think I already did 2 or 3 questions from that, but great. Okay, now let's move on to the important topic. Group actions on sets. Okay. Are we all good? So try to see that. Try to think about this. It's not think about this problem. You're convinced of that if lambda G is odd, then this homomorphism is surjective. If for some G lambda G is odd, then this homomorphism is surjective, right? Are you convinced of that? Yes or no? Yes. Pardon me? Minus 1. Yeah. If it's even. If this sign is even, right? If the permutation is even, right? You write a permutation in terms of transpositions, and then you see how many transpositions you can write this as. Okay? The alternating group, remember that? Yeah. Okay. Great. Yes.
Can you get the plus 1 with the identity?
Yeah. The identity is always an even function. Right? The identity is always an even permutation. So you have +1. If you have an odd permutation, then you have a -1. Then the kernel of phi has size G/2 if G is finite. By the first isomorphism theory, right? G modulo the kernel of rho would be isomorphic to rho of G, which is ±1. So the order of G modulo per phi per rho is 2. So rho would have index 2. Okay? By the first isomorphism theory. Anyways. Okay. Now we start the most important part of group theory of this question, which is called group actions on sets. Okay, so in homework 4, we have proved something with conjugacy classes. That, first of all, that a group G is a disjoint union of equivalence classes. Using this, well, how do we prove that? First, we defined an equivalence relation. We said that two elements being conjugate is an equivalence relation on G. Right? Then, using this, we partition G into a union of equivalence classes. Right? If you remember that. Great. Then, we said that an equivalence class has the same size as G modulo Cx. The set, so G is conjugacy, so X is conjugacy class. Then there exists a bijection from G mod Cx, the equivalence class of X, that sends a coset GCX to Gx the inverse, where Cx is just the set G and G such that Gx G inverse is equal to X. If you remember this. The goal here will be to generalize this. This goal, the goal of group actions, was not the goal. Well, we will see how to generalize this to arbitrary, well, not to arbitrary, to some actions. This is called an action, basically, of a group G on a set S. Okay, so this is the main goal. You will notice that the proofs, the steps I'm taking here, are similar to the steps in the homework. Okay, so you'll notice it's kind of the same, order, or not necessarily order, the same steps I'm taking. Okay, great. The definition. Let S be a set and G be a group. Then an action of G on S is a function. G cross S to S that sends a pair GS to G star S. I'll call this star. I'll call this function star. It takes an element of G, an element of S. It gives you an element of S. I'll call this element G star S, such that EG star S is equal to X for all S in S, and G1 star for all G1 G and S in S. Okay, this is just a definition. Star is just a function from G cross S to S. Now let's give a simple example. Let's give examples. And we can see how this can be generalized. Let's give a very simple example. One, let S be a set, and the symmetric group be a symmetric group on S. Well, consider sim S. So what is a symmetric group on S? It's just the bijections from S to S. Then I can find an action. Sim S. Well, we say G acts on S basically. They're an action of the function. We say G acts on S. Or another word that S is a user. Now, sim S acts on S in a very obvious way. If you take sigma in sim S, and you take little s and s.
Wait, what does it mean to be a G set?
This means that G acts on S. Okay, we say that
No,
S
but
is
like on the parenthesis.
here.
G set.
Means that G acts on S. So there is an action of G on S. It means that we say that G acts on S or that S is a G set. That's just a name. Okay? Great. Now, how does sim S act on S? What is a most natural way to define sigma star S? You have a function on S and you have an element of S. What could you do? I have F and I have X. What do I do? F of X, right? Sigma of S. G, sim S, the group. S is in big S, and sigma of S is in big S. Now let's prove that it satisfies the action. The action properties. Now, what's the identity of sim S? Identity of sim S, what is that? It's just the identity function on S, right? What's ID star of S? So let S be an S. ID star of S, this is just the identity of S on S. It's just S. Now let's prove the other one. Let sigma 1, sigma 2 in symmetric on the symmetric group of S. What is sigma 1 star sigma 2 star of S? This is just sigma 1 of sigma 2 of S, which is just the composition of sigma 1 sigma 2 applied to S, which is just sigma 1 of with sigma 2 star S. Okay, this is a group action. Just to set the axioms. You have to check the definition. Let's do one more. Let's look at conjugation in G. Here, my set S will be G. Conjugate group. This is did I write one here? Let's write it. Conjugate group. And let S equal G. So I need a function from G cross G. G. Well, let's take conjugation. I take Gx, and I get back Gx, G inverse. So G star X really. G star X is Gx, G inverse. Let us show that it satisfies the axioms or the definitions of a group action. I have them up there. So now your set S is G, really. Okay, so let X be in G. What is EG star X? This is EG X, EG inverse, which is X. So the first property is satisfied, right? You see that? Everybody, do you see that?
Yes.
Now let's look at the second property. Let G1, G2 be G. What is G1 star G2 star X? Well, this is G1 star G2 star X. What is that? It's just G2 X G2 inverse. By definition of the star. Now, what is G1 star that? This is just G1 G G1, G2, X, G2 inverse, G1 inverse. Right? Everybody, look at the definition here. Yes.
Are you writing that something happens but nothing happens?
What do you
Like
mean?
you just kind of put
No.
the parentheses down and then it just
Exactly. Well,
shows what happens.
Exactly.
But
yeah, exactly.
nothing
you show-
happens.
What do you mean nothing?
There's just a bunch of composition.
Exactly. Well, it's the compositions here are made so that it works, right?
It works.
Okay. What is that?
What does it mean for all those compositions to happen?
It means a group action, right?
Yes.
This is the definition. Okay. Now, what is this? This is just G1, G2. Okay. So checking something is a group action is just going through the definitions. Just as if you have checked something is a binary operation, you have to go through the definitions. Checking something is a group actions, you have to go through the definitions. Okay? You have a very nice thing is that the most important property means that if you let G2 act on X and G1 act on X, it's the same thing as if G1, G2 acted on X. Okay, now what is this used for? This is a good question. This is the most important question. What is this used for? How do we work with this? Let's define. Okay. Let S be let. The orbit of S by orbit is defined to be the set G star S and G is in G. Let's get back to the conjugation. Okay. The idea is that let's look at conjugation. What is the orbit of an element X in G? This is just G star X as G is in G. So if I'm taking G star X to be the conjugation, what is the orbit of X? It's G X G inverse as G ranges in G. What do we call this?
Conjugate.
The conjugacy class of X, correct? Of X. Okay. I have an action which is a function from G cross S to S, and I define an orbit. What's another obvious action of G on itself? If you take the binary operation, let's say G times H and gives you back GH, isn't that a group action of G on itself? Check the axioms. So identity times G, identity times X, what do you get? X. Now G1, G2 times X. This is the composition law, the associativity rule. Okay? So really we're kind of generalizing operation, binary operation on G in some sense. Okay? Are we good here? Okay. You just have to sit down and write down show that the properties hold. Okay? Should I give the example of one more action? Should I let's give an example of one more action. It's another example. So let S be G, and an action from G cross G to G that takes G X, when G star X is just equal to GX. So really, my star is just the circle operation, the group law. This is a group action. What is EG star X? This is just EG X. It is just X. What is G1 star G2 star X? G2 star X is just defined as G2X. And so this is G1 star this. What is that? This is just G1, G2 times X. It's just G1, G2 star X. Star is just a function from G cross X to S. And that's it. Okay. Now what is the orbit of X? You know, I'll let you work this out. The orbit of X is just Gx as, as G is in G.
Does that mean it's the right coset?
Right?
The right coset by X?
In here?
Yeah, is equal to Gx. Yeah, it's not big Gx.
Big Gx, what is that? Very good. What is that?
The right coset.
What is that?
It's G.
Right?
G.
This is just G.
Yeah.
Right? Now the good thing is that what if H is a subgroup of G? And you let, okay? That's a good question. Sorry, this is just, what is it? Yeah, Gx. Yeah, that's fine. Okay, great. So this is a group action. It's not complicated. It's just a bunch of definitions and that you have to check. Okay. Now, the first time I saw this, in my algebra 1, I had a question on group actions. Totally bombed it. Nothing. Was on 10 marks. 0. Okay. 0, actual 0, yeah. 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 I don't know.
What do you mean you don't know?
It got better with time, Algebra 2 was good.
What did you first do between the moment you almost failed the class?
I didn't fail the class.
No, you were here, but
I didn't fail the class.
how did you get in between two?
I just worked harder.
No.
I just worked harder. You work harder, and you read your notes. But anyways, when you read your notes, you will start doing well. Just practice. Yeah, that final just. Maybe if I remember the questions on it like this was so remarkable that I still 10 questions with a bonus one. I remember them as if it was yesterday.
How long was it ago?
Long time ago. Okay.
Are we talking in months or in years?
Or years. Okay, so let's continue. And algebra is a very nice subject, and you'll learn to like it. First one you don't like it, but the second one, most of the people do well in algebra 2, so you like it. Algebra 3 and 4 are awesome. Higher algebra 1 and higher algebra 2 are great. Okay? Yes. Yes, it is. It is. Pardon me? Algebra 2 is more like linear algebra, but you will see like abstract structures like that. Yeah. Okay. Now, the stabilizer, another definition. Let S be an S. the stabilizer of S is the subset of G, we denote it by stab S, defined by G is in G, and G star S is equal to S. These are just like weird definitions, but why is it called stabilizer? G star S is equal to S. So when little g acts on S, it doesn't change. So let's get back to conjugation. And I didn't do that horrible. I got A minus. So but I can tell you, I got, so it was like 50% until the midterm. I got that maxed out, like 50 on 50. And then I got an A minus after curve. So like A minus after curve. So I like got like something like 55 on the final. 57, 58. Because 60, right? If you get 50 and you get 60, that gives you 80, right? If the final is 50% and you get 60% of the final, that gives you 30, right? 50 plus 30 is A minus. So it got curved a bit by like 2-3%. And I managed to make it. Okay. So what's the stabilizer of X in a conjugacy class? This is just stab X is just G and G. But then G star X is X. Let me write this down. Anybody thinking of taking algebra 3 and 4? Those are very, very, very cool courses. It's not part of my curriculum. So what is stab X? It's just B and G, such that Gx, G inverse is equal to X. Right? This is just Cx. Agree? Bring the X inverse on the other side. It's just the G and G that commutes with X. Cx. Peter, are we good? Yeah. Everybody? Is it clear? It's a bit difficult. It's a bit too abstract. But I'm generalizing conjugation to other type of actions. I mean, it's clear on conjugation. This is it, right? What is G star X for conjugation? Gx, G inverse, right? So just decide Gx, G inverse is equal to X. This is the stabilizer of X. It's tough, huh? It's not the most wonderful, but you will see that it allows to prove very, very, very strong theorems. Okay. I mean, was assignment 4 okay? Assignment 4, was it okay? Yeah, assignment 4 was a bit tough, but you see that it's the same steps. Now, what did I prove in assignment 4? What did I ask you? That C of X is a subgroup. So here, what is the next step? That stab S is a subgroup. Yeah, here. Stab S in the subgroup of G down. So what is G star X? This is just by the group axioms. What is that? Just as S. Hence, EG belongs to stab S. Now let G1, G2 belong to S. Belong to stab S, sorry. I need to show that G1 star G1, G2 belongs to. I'll keep this one here. Need to show that G1, G2 belongs to S. So I need to show that G1 star G2 S. I need to get that this is equal to S. Now G2 belongs to stab S. Look at the definition of stab S. It's G star S is the set of G and G such that G star S is equal to S. If G2 belongs to stab S, what is G2 star S?
S.
S. This is G1 star S. Now G1 belongs to stab S. What is G1 star S?
S.
S. Very good.
What the point?
So what? So G1, G2 belongs to stab S.
Maybe you wanted to write G1, G2 before
Right.
together. S.
No, I already have that. I already know this is G1, G2 star S. You need to show that. Oh, you mean like this one? Right. Yeah. Yeah. You're right. Thank you. Okay. Thank you. Thank you. Great. I mean, I'll just finish the G1 inverse. Can I finish it up?
Yes.
Just the G1 inverse, just so that we don't get back to that. But it's equal to S. G1 inverse star G1 star S is equal to G1 inverse star S. We'll star both sides. Now G1 inverse G1 star S. This is just G1 inverse. G1 inverse G1 is the identity star S. It's just G1 inverse S. So G1 inverse star S is S. So G1 inverse belongs to star S. Hence, star S is a subgroup of G. Okay, so I just need to talk 2 seconds about the midterm if you're interested. The midterm is yeah, I don't know if I'm gonna give like more hints, but please focus on Lagrange's theorem. Okay, like Lagrange's theorem and its corollaries. Okay, focus on them. Make sure you know how to do every proof from Lagrange and Coset. Okay, you're gonna be examined on them. Okay, in addition to cyclic groups and the Euclidean algorithm and Fermat or Euler's theorem. Okay, so again, no conjugacy classes, no symmetric group. It just what I said it would be. Okay, so but again, I've been asked. Lagrange includes everything: right cosets, left cosets, the proof of Lagrange, the parts of the proof of Lagrange, the corollaries of Lagrange. Okay, and the results you can do with Lagrange. And assignment 6, question 1 is very important as well. Yes. I might ask you parts of it. I might ask you part of it. Prove that 2 left cosets are in bijection, for example. Okay. Yeah. No, I said that there are only 2 questions that I can put on the midterm from assignment 6. I will post the solutions to these questions. Okay. Great. See you all.
What do you mean assignment 6?
The one that is